Welcome back. Today we are diving into the best configuration for the Z-axis concept I recently introduced in this channel. After reflecting on the fantastic feedback from my peers' video about this prototype, I decided to run some quick finite element analysis models based on a box concept. This digital prototyping involves preparing two options, one using 2 rails and another one using 4 rails. The key factors we are looking are the deflection, assuming that the plates are made out of aluminum. Given the capacity of the stepper motor, the weight should not exceed 5 kilograms. To be safe, I'm keeping it under 3 kilograms. Another important consideration is the dimensional capacity of the current machine, as I'm to machine the parts myself. The current dimensions are 215 millimeters on the X direction, on Y 180 millimeters, and on the C height we have 100 millimeters. Here are the deflection results with the spindle extended 100 millimeters and having a force of 49 newtons applied at the tip of the spindle. With the option of 2 rails, we have 9 microns. With the option of 4 rails, we have 4 microns. This represents a 55% of improvement in between the 2 rails and the 4 rails option, measured at the tip of the linear guide rail as shown on my previous short video, linking here. But wait, there is more. By adding these 2 plates at the top, covering at least the height of the carriages, we are obtaining a deflection of 1.4 microns, measured at the tip of the rail. Remember, FEA analysis is just an approximation. It is not expected to be super precise, but I hope it is going to be. So one of the things that I take care is the behavior of the analysis should be as behaving as accurate as in real life we expect. So let me show you the animation of the rails and the carriages. Okay, so as you can see, the carriages are set to have a sliding relation against the rail. So they are sliding a little bit. That is something that we expect. At the end, the y-axis constraint is given by this point with this rigid connector connected to the top of the plates, because that's where the nut for the lead screw is going to be placed. So at the end, that's the only point that is going to be constrained in the Z-axis, right? So we should be able to see this type of sliding of the rails while the thing is trying to deflect on the x-axis. Because of the x-axis, I mean force, right? So looking closer to this other one, we can see exactly the same behavior. So we are having a very close to real life situation. The other aspect is that I'm not having a connection in between these plates, top plates, and the box at the bottom. So they should be capable to separate a little bit. That's expected from the setup that I have. I do not have plans to connect those two together. It's going to be a little bit tricky, and also adding some weight to the assembly that actually I need to take care that we are not going to exceed the 5 kilograms as I mentioned earlier. Other very useful result is the reaction forces at the carriages. So as you can see, I'm fixing the carriages with a rigid connector, and that connector is having at the center the constraint itself. So checking the reaction, we can have, by the maximum loading of the 49 newtons in this point, you can see 13 newtons at the force, total force, and in the case of the moment, we have a very small moment, just 685. Looking at one of the carriages here at the top, we can see that our max force is 9 newtons, and the moment is a little bit larger, but not a big concern. 2,729. But if we look at the datasheet of the manufacturer, we are far so good with these numbers. So as you can see, newtons on the static load rate is in the range of the 3,720 newtons, while we are just at the most in 20. While talking about the moments, we have 24 or 23 Newton meter, and that in Newton per millimeter, which is the unit that I'm using in software, you can see that we are way too far from getting in troubles, right? So we get something around 2,700, and the product itself can handle way much more. So this gives me confidence on the selection of the rail, but also is a big question if we should take another look to the product that have been selected and maybe use a smaller guide rail. Another consideration is that this is not the total deflection of the machine. This is just the z-axis. So we need to include the x-axis in our results to see the final deformation that we are going to have under max capacity of the stepper motors. This is something that I will show in the next video.